In today's tutorial, we will talk about vector space. And first, we will talk about the definition of vector space. Definition: a vector space V is a set of vectors that can be added together. It is the vector addition and multiplied by numbers. It is the vector multiplication without leaving the space. It means the vector added or multiplied the resultant vector also in the set of V. A vector with n elements, V equal to bracket V1 to Vn, where V is a vector space of order n and m times n dimension m times n is a order of the matrix. M is the column and n is the row of the matrix. For example, R2 is a vector space containing all two dimensions vectors with vector V equal to bracket x and y. And now I will introduce a concept about Rn vector space. N is the number of dimensions, and Rn vector space includes every vector of the same dimension. Adding any vector or scaling any vector in the space must be possible. We can do infinite addition or multiplication in the Rn vector space. Second, I will talk about the operation. First is the vector addition. Vector addition means if A and B are any vectors in V, V is the set of vector space, then the sum A plus B belongs to V. The first law of the vector addition is the commutative law. For any vectors A and B, A plus B equal to B plus A. Look at the graph. There are two opposite direction vectors of A and B, but their resultant vectors is also the same. It's the same magnitude and the same direction. The second law is the associative law. For all vectors A, B, C in set V, A plus bracket B plus C equal to bracket A plus B plus C. And the third law is the additive identity. For set V contains an additive identity element denoted by 0, such that for any vector V in set V, 0 plus V equal to V and V plus 0 equal to V. And the last law of the vector addition is the additive inverse. For each vector V in vector space V, x plus V equal to 0 and V plus x equal to 0 have a solution V equal to minus V, and x is called an additive inverse of V. Look at the graph. Both vectors have the same magnitude but in opposite direction. It means the other vectors is the additive inverse of V. And thirdly, we will talk about the operation about scalar multiplication. The scalar multiplication is about if V is any vector in set V and C is any real number, then the product C dot V belongs to the set V. V is the vector space. And the first law is the distributive law. For all real numbers C and all vectors A, B in vector space V, C dot bracket A plus B equal to C dot A plus C dot B. For example, when C equal to 2, 2 times bracket A plus B equal to 2 times A plus 2 times B. The graph shows the result. The second law is also the distributive law. For all real numbers C and D and all vectors V in vector space V brackets C plus D dot V equal to C dot V plus D dot V. For example, when C equal to 2 and D equal to 3, brackets C plus D dot V equal to 5V and C dot V plus D dot V also equal to 5V. And the third law of the scalar multiplication is associative law. For all real numbers, C and D and all vectors in vector space V, C dot bracket D V equal to C D dot V. For example, C equal to 2 and D equal to 3 and V is unit 1. Left hand side of the equation is equal to the right hand side and equal to 6. And the last law of the scalar multiplication is the unitary law. For all vectors V in vector space V, 1 dot V equal to V. After talking the vector addition and scalar multiplication of the vector space, and now I will introduce some examples to consolidate the theory of vector space. Example 1. Show that the set of 2 times 2 matrix with real number entries is a vector space with dimension 4, such as R4. First, I will introduce a matrix with real number A, B, C, D. Since for the first law is the scalar multiplication, 2 vector in the vector space, the sum of the 2 vector is also in the vector space. So introduce A, B, C, D, and E, F, G, H, and their result is A plus E, B plus F, C plus G, and D plus H. And introduce a real number set to have the scalar multiplication with A, B, C, D. The result is set A, set B, set C, set D. Since the result of the 2 matrix and the A, B, C, D and the D, F, G, H, also the constant Z is also in the vector space. So in this example, we can conclude matrix A, B, C, D is R4. The second question is so that the following example is not a vector space, which X, Y, Z is the matrix in the vector space R3 and X, Y, Z is real number, and X plus Y plus Z is equal to 1. By choosing 2 sets of solution, the first set is 1, 0, 0, and the second set is 0, 1, 0. The vectors addition of these 2 vectors is 1, 1, 0, which is not the solution set because 1 plus 1 plus 0 is equal to 2. Since for the first law of the vector addition in the vector space, 2 vectors when they are added together, the result is also in the vector space because the vector cannot leaving the space. So this is not a vector space. The third example is proof or disproof that R2 is a vector space of the following case. X and Y is the matrix in the R2 and X and Y is any real number. The second condition is X plus 3Y equal to 4 and 2X minus Y equal to 3 and 6X plus 4Y is equal to 10. And the solution is it is empty because there is no solution in the second condition. Based on the third law of addition, it is the additive identity. This R2 vector space is not a vector space. After the previous example, there are some questions to test how you understand this topic. Here is the question. There are 2 questions, and the first question have 2 parts. This is the second question. Here is the solution. Both questions are similar to the example. It is the end of the tutorial. Thank you.